It is 4:17 in the morning when the first turbine shifts load. The sound doesn't travel far, not at first. It begins inside the powerhouse as a low-frequency vibration, something between a hum and a pressure change, something you feel in your sternum before your ears register it. The concrete walls here are 2.4 meters thick. The floor is bolted steel over bedrock, and still the whole structure trembles slightly when the generator comes online. Outside, it is minus 23 degrees Celsius. The reservoir behind the dam holds 61.7 billion cubic meters of water. That is not a number that fits easily in the mind. It helps to say it differently. Enough water to cover the entire state of Connecticut under 30 meters of liquid. Enough weight to measurably depress the bedrock beneath it. Enough pressure at the base of the intake structure to collapse a non-reinforced chamber in under 4 seconds. This is La Grande 2, and the centerpiece of the James Bay Hydroelectric Complex. And right now, in the cold dark of a Quebec winter, it is feeding 5,328 megawatts of electricity into the grid, quietly, precisely, without ceremony. The operator on duty doesn't look up from his console. He has been doing this for 19 years. The readings are nominal. They are almost always nominal. That is the point. To understand James Bay, you have to understand the scale of the problem it was designed to solve. Quebec in the early 1970s was a province with ambition and a growing industrial base, but its electrical future was uncertain. Oil prices were volatile. Thermal generation was expensive. Nuclear was politically complicated. What Quebec had in extraordinary abundance was water. The James Bay watershed covers 350,000 square kilometers of boreal forest, muskeg, and exposed Canadian shield. It receives snowpack that melts slowly across spring and early summer, feeding hundreds of rivers that funnel north toward James Bay itself. The rivers were not navigable. They were not scenic. They were enormous, fast, cold, relentless. Hydro-Quebec's engineers looked at the La Grande River, 893 kilometers long, draining a basin the size of Italy, and made a calculation. If they could capture even a fraction of its annual flow, they could generate more electricity than Quebec could consume for decades. The question was not whether to build. The question was how to move an entire construction civilization into one of the most remote landscapes on Earth and keep it alive long enough to finish. The first equipment convoy reached the site of LG2 in 1973. There were no roads. Hydro-Quebec built them. 620 kilometers of all-weather access roads, carved through permafrost and muskeg, some sections requiring continuous maintenance just to remain passable. Winter construction was the only practical option for certain phases. The ground, and when frozen, could bear the load of the cranes. In summer, sections of muskeg became almost liquid. At peak construction, the James Bay project employed 18,000 workers simultaneously. They lived in purpose-built camps. James Bay's construction villages had cafeterias, dormitories, recreation facilities, medical stations, and electrical systems of their own. Some camps housed over 5,000 people. Supply flights landed daily. Everything, from welding rods to bread flour to turbine shaft seals, arrived either by road convoy or by air. The logistics operation required its own management structure. There were engineers whose entire job was scheduling concrete pours, others who tracked bolt inventories across 11 active construction fronts, workers who specialized only in powerhouse floor leveling, a precision task critical to turbine alignment, where a variance of 2 millimeters across a 40-meter floor could cause long-term bearing wear. Nothing about this project was improvised. Everything was pressure tested before the pressure arrived. The La Grande 2 dam itself is a rockfill structure, a type chosen deliberately for this terrain. Concrete gravity dams require foundations with minimal movement. The shield bedrock here is stable, 3.8 billion years old, among the oldest exposed rock formations on Earth. But surface soils and frost conditions made concrete placement complicated in certain zones. A rockfill embankment dam uses the weight and mass of compacted material to hold back water. The dam's central impervious core, a thick zone of glacial till compacted to near zero permeability, is the real barrier. The rock on either side provides weight and stability. The main dam at LG2 is 2,835 meters long. Its crest stands 168 meters above the original riverbed. During construction, engineers placed compacted material at rates exceeding 150,000 cubic meters per week during peak periods. A compaction crew worked in overlapping shifts. Every lift of material, each layer typically 30 centimeters thick before compaction, was tested for density before the next layer went down. Skip a test, miss a void, and years later you might see seepage. Seepage becomes flow. Flow becomes failure. This is why rock-filled dam construction is slow. Not because of the material, because of the verification. The powerhouse is where the river becomes electricity. At LG2, the powerhouse is embedded inside the rock of the north bank of the La Grande River. Underground powerhouses are sheltered from ice loading, they minimize surface footprint, and the surrounding rock provides structural support that reinforces rather than constrains the machinery. The excavation for LG2's powerhouse was, at the time of its completion, one of the largest underground excavations in the world. The chamber is 483 meters long, 26 meters wide, and 47 meters high. To put that in physical terms, you could stand a 15-story building inside the powerhouse cavern and still have clearance at the top. Inside that chamber, 16 Francis turbine generator units are arranged in a row. Each unit is a vertical shaft machine. Water enters from above, through the penstock, a sealed steel pipe, in up to 10 meters in diameter, that conveys pressurized flow from the reservoir, and strikes the runner, the curved steel wheel at the turbine's heart. The runner spins. The shaft transfers that rotation upward to the generator. The generator converts rotation into electricity. It is, conceptually, the same process that drives a small hydro wheel on a country mill stream. The physics is identical. The scale is simply different by a factor of several hundred thousand. Each unit at LG2 generates 333 megawatts at full load. Total installed capacity at LG2 alone, 5,328 megawatts. That single station could supply electricity to a city of 4 million people. The penstock. It is easy to overlook the penstock. It is inside the rock, hidden from any aerial view, not photogenic in the traditional sense. But the penstock is where the violence lives. Water in a reservoir is patient. It sits, it presses, it waits. The moment a gate opens, even partially, that patience ends. At LG2, the head of water above the turbines reaches approximately 137 meters at full reservoir. Water under that kind of pressure column moves with force that makes industrial analogy difficult. The flow through a single penstock at full gate opening is around 300 to 400 cubic meters per second. That is enough water to fill an Olympic swimming pool in under 10 seconds. The penstock steel must contain that flow and direct it precisely. Any misalignment, any weld failure, any corrosion that goes undetected long enough to compromise wall thickness, and the penstock becomes a catastrophic release mechanism pointed directly at the powerhouse interior. Hydro-Quebec's inspection program treats penstock integrity with the same formality as a structural audit. Inspection teams enter the penstocks during planned outages. The units are drained. When the steel walls, still slick with residual moisture, smelling of iron and cold, are walked inch by inch. Ultrasonic thickness gauges are pressed against the steel. Readings are recorded. Anything below threshold triggers repair before the unit is returned to service. The team doing this work is small, usually 4 or 5 people. They work in cold and confined space, in headlamps with reference charts and calibration tools. They are not famous. They keep the penstocks intact. And the spillways at LG2 are the system's pressure relief valve. During high inflow periods, spring freshet, heavy rainfall events, years of above-average snowpack, the reservoir must be controlled. The turbines can only absorb so much flow. When inflow exceeds generation capacity, water must be released in a controlled manner. The LG2 spillway is a concrete chute structure on the north side of the dam. At full opening, it can discharge 16,280 cubic meters per second. To understand that rate, It exceeds the average discharge of the Rhine River in Germany at high water. The discharge channel is lined with reinforced concrete. Even so, the energy of water at that velocity is erosive. High-velocity flow over concrete creates cavitation, microbubbles that collapse against the surface with localized pressures exceeding 100 atmospheres. Over years, cavitation damage looks like the concrete has been eaten away from inside, pitted, hollowed, weakened. Spillway inspection is a specialized field. Inspectors wear hard hats and waders and move through damp, echo-filled concrete channels with flashlights and measurement tools. They look for spalling, cracking, pop-outs, exposed rebar. The sounds in a spillway channel at low flow, a thin sheet of water moving over textured concrete, are unlike anything in most people's experience. A flat, dense resonance that seems to come from every direction at once. Damage found early is patched. A polymer-modified concrete, epoxy injection, steel fiber reinforcement. Damage found late means a longer repair window, a longer outage, a disruption to generation schedules that ripples through the provincial grid. Early is always better. North of LG2, the La Grande complex extends in both directions along the river. LG1 operates downstream, near the river's mouth at James Bay. LG3 and LG4 are positioned upstream, each capturing the fall of the river across successive sections of the watershed. Diversion structures on tributary rivers, the East Main, the Opinaca, the Caniapiscau, redirect water that would otherwise drain south into Hudson Bay, channeling it instead into the La Grande system. These diversions increase the La Grande's regulated flow substantially. The river as it now operates is not the river that existed before 1975. It carries water from multiple watersheds. Its seasonal variation has been flattened, not eliminated, but reduced by reservoir storage. Spring freshets that once sent flows surging are now absorbed into the reservoir, stored, and released according to demand, not season. This is the core function of a storage hydroelectric system, decoupling electricity generation from precipitation timing. Winter in Quebec is when electricity demand peaks. Heating loads surge. Industrial processes run full capacity. The grid requires consistent and dispatchable power at exactly the moment when no solar generation is available and wind is unreliable. Water stored in summer, delivered as electricity in winter. This is what the James Bay reservoirs do, every year without exception. The control room at LG2 is quieter than most people expect. The machines are several levels below. The acoustic separation is effective. The room itself is a study in controlled information density, a long console of monitors, flow gauges, unit status displays. See alarm panels. The lighting is steady, neither harsh nor dim. The temperature is regulated. The operators who work these shifts are trained in the system dynamics that take years to fully internalize. They understand the relationship between reservoir level, turbine loading, tail race water elevation, and grid frequency. They know that increasing load on one unit at the wrong moment, when the grid is already frequency sensitive, can create a cascade effect that trips a protection relay downstream. So they also know the sound of a healthy machine. A turbine bearing running within a specification makes a particular sound through the structure of the building. A slightly different sound, higher pitched or with a resonance that doesn't belong. And an experienced operator will investigate before the vibration sensor flags it. There is a body of knowledge in this control room that lives in the people, not the system. When operators retire after 20 or 30 years, a structured knowledge transfer process begins months before their last shift. Apprentices shadow them. Walkthroughs of edge case scenarios, historical incident logs reviewed together, the reasoning behind non-obvious procedures explained and documented. The system's reliability depends on the machines, and it depends equally on the humans who understand the machines in ways that no monitoring software fully replicates. Maintenance at a facility this size is not a reactive discipline. It is a calendar. Every Francis turbine unit at LG2 follows a major overhaul cycle. Typically, this means a full inspection of the runner, guide vanes, spiral casing, and draft tube every 12 to 15 years, with intermediate inspections and minor maintenance at shorter intervals. When a unit comes down for major overhaul, it is out of service for months. The runner alone weighs between 250 and 350 tons. Removing it requires purpose-built lifting equipment, precision rigging, and a team with specific competencies. The runner is lifted clear of the turbine casing, moved laterally, and positioned for inspection. The blades, curved steel surfaces machined to exacting tolerances, are examined for cavitation damage, cracking, erosion. Any surface damage is repaired by specialist welders using controlled heat input to prevent distortion. The guide vanes, which direct water flow onto the runner at the correct angle, are examined for wear and precise movement. In the vane stems pass through sealed bushings. Bushing wear is measured. Seals are replaced on schedule whether they show wear or not. The philosophy is not to wait for failure. The philosophy is to eliminate the conditions that produce failure. This requires a certain discipline. The discipline of maintaining something that appears from the outside to be working perfectly. It is always easier to defer maintenance on something that isn't broken. At James Bay, that temptation is managed by procedure. In the transformer hall, adjacent to the powerhouse, the generated electricity is stepped up in voltage for long-distance transmission. The generators at LG2 produce power at around 13.8 kilovolts. This is a working voltage, useful at close range, but inefficient for transmission across hundreds of kilometers. To move power from James Bay to Montreal, a distance of over 1,000 kilometers, Hydro-Quebec uses its own high-voltage direct current transmission system. HVDC was chosen over alternating current for this specific corridor for technical reasons. At very long distances, the capacitive losses in AC transmission become prohibitive. DC transmission, once converted, carries power more efficiently over extreme distances. Whilst the trade-off is complexity at the conversion stations. Large facilities filled with thyristor valve banks, smoothing reactors, and precise control systems that manage the conversion from AC to DC at the sending end and back again at the receiving end. The James Bay HVDC lines operate at plus or minus 450 kilovolts. The pylons carrying these lines across the boreal forest are spaced for extreme wind and ice load conditions. Freezing rain, the particular hazard of Quebec winters. High can coat conductor cables with ice accumulations weighing tons per span. The cables are rated for this. The pylons are rated for this. Once every several years, an ice storm of sufficient severity challenges the ratings. Line crews operate in those conditions, working at elevation, in freezing rain, on steel structures that conduct cold better than almost any other material. They know the work. They do the work. The reservoir system of James Bay operates as a unified hydrological machine. Reservoir Kaniapascau in the northeast stores water from the Kaniapascau Basin, an area of 98,000 square kilometers, roughly the size of Iceland. This water is held, released in controlled quantities through the diversion infrastructure, and added to the Lagrange system over the operating season. Reservoir Opanaka, to the south, captures flows from the Eastmain and Opanaka rivers and routes them north. Each reservoir is monitored continuously. Water level, inflow rate, temperature gradient, ice thickness in winter. Ice is a significant operational variable. In the deep cold of January, the surface of a James Bay reservoir will freeze. The ice can reach 1.2 meters thick. This ice does not impede operations. The intake structures are positioned well below the ice-affected surface zone. But it does affect the visual interpretation of satellite imagery, the behavior of floating debris, and the logistics of any surface access required for remote structure inspection. Ice out in spring is managed carefully. As temperatures rise and ice begins to break up, large sheets can move toward intake structures and debris barriers. Maintenance teams monitor these events. Operational controls, gate positions, flow management, are adjusted to minimize the risk of ice ingestion into turbine intakes. Nature does not stop operating because the machines are running. The machines must account for nature every day. It's the grid that James Bay feeds is the Hydro-Quebec interconnected system, a network that extends across the province and connects to neighboring grids in Ontario, New Brunswick, New York, Vermont, and Massachusetts. Hydro-Quebec is not only a generator, it is a grid operator, a transmission authority, and an electricity exporter. On a typical January evening, when Quebec's demand peaks, the James Bay Complex may be generating a substantial fraction of the province's entire electrical output and simultaneously exporting surplus to the northeastern United States, where peak demand coincides with Quebec's cold snaps. This export capacity is commercially significant. Surplus electricity in hydro systems has near zero marginal cost once the infrastructure is built. And the marginal cost of generating one more megawatt hour at LG2 is essentially the cost of the water flowing through, which is zero. What limits generation is not cost, but reservoir level, turbine availability, and transmission capacity. The economics of James Bay are front-loaded. The capital cost was enormous, spread across decades of financing. The operating cost is comparatively modest. The asset, properly maintained, will generate electricity for a century. This is the financial logic of large hydroelectric infrastructure. The investment is geological in scale. The returns are also geological in duration. There is a diver inspection program that runs on James Bay infrastructure. Not all of it. Most of the critical components are accessible during planned outages, when units are dewatered and maintenance teams can walk directly into penstocks and intake bays. But some structures require underwater assessment while remaining in service. See intake trash racks, gate seals at depth, concrete surfaces below the normal water level. The divers who do this work are commercial diving specialists. They do not dive in clear water. The reservoirs of James Bay are tinted, glacially derived with suspended fine particles that limit visibility to 2 or 3 meters in most conditions. Working at depth on large metal structures in limited visibility requires a specific skill set: tactile inspection, methodical grid patterns, constant communication with a surface tender. Dive operations at hydroelectric facilities carry a category of risk not present in marine environments. Current. Even at some distance from the active intake structures, reservoir currents can be significant during high flow periods. Dive plans must account for current direction, intake proximity, and escape routing. A diver swept toward an active intake is in a situation with a very short resolution window. When the protocols around this are rigorous and non-negotiable, no dive proceeds without surface communication. No approach to intake zones without precise exclusion distances confirmed. No deviation from the dive plan without surfacing and rebriefing. The divers who work these conditions are experienced. They have gone through progressive exposure, open water work, then industrial, then facility-specific training for each site. They describe the work as methodical, and which is exactly what it needs to be. By 2001, the second phase of the James Bay project, long delayed, contested, and ultimately reconfigured, had produced the East Main Complex on the East Main River. The original James Bay plan, as conceived in 1971, had been far larger. It included Great Whale, a second major river system north of La Grande, and the NBR, Nottoway, Broadback, Rupert, complex to the south. Political, legal, and financial pressures through the 1970s, 1980s, and 1990s suspended these components. What was built was built. What was deferred remained deferred for decades. Eventually, the East Main 1 and East Main 1A powerhouses, along with the partial diversion of the Rupert River, were completed in the 2000s and 2010s. These additions brought incremental generating capacity and extended the reach of the La Grande watershed's regulated system. Each addition required its own planning, permitting, agreement, and construction cycle. The construction of East Main 1A, completed in 2012, added 768 megawatts of capacity. The Rupert diversion was contested. Lengthy negotiation between Hydro-Quebec and Cree communities produced the Pays de Brave Agreement in 2002, a framework that restructured the relationship between the province and the Cree Nation, providing economic participation and governance rights in exchange for agreement on the East Main developments. And the politics of this project cannot be separated from its engineering. They never could be. But this is an operations story, and so we return to what the machines do. They run. Every hour of every day, winter and summer, grid frequency maintained, water converted to electricity, electricity delivered south. The full La Grande complex, LG1, LG2, LG2A, LG3, LG4, Brisset, Laforge 1, Laforge 2, and the East Main additions represents a total installed capacity of over 16,000 megawatts. And to put that in context, that is more than 3 times the generating capacity of the Hoover Dam. It is roughly equivalent to 16 nuclear power stations, built in one of the coldest, most remote regions on Earth, with roads that didn't exist before 1973. The scale is not a historical achievement. It is a present tense operational reality. Right now, as you watch this, water is flowing through turbine runners in underground powerhouses on the La Grande River. The electrons are moving south through HVDC lines toward Montreal, toward Albany, toward Boston. The operator on duty at LG2 is watching the console. The readings are nominal. They are almost always nominal. That is the discipline. Hydro-Quebec's ongoing maintenance investment at the La Grande complex runs into the hundreds of millions of dollars annually. The structures are aging. LG2 was commissioned in 1979, more than 4 decades ago. An aging infrastructure requires not just routine maintenance, but strategic assessment. Which components are approaching end of life? Which upgrades will extend the asset's operating horizon by decades versus years? Where are the hidden vulnerabilities that haven't yet appeared on monitoring dashboards? This is the work of a group of engineers who specialize in asset condition assessment. They review inspection records, vibration histories, thermal imaging data from generator windings, oil analysis from turbine bearings. They build degradation models. They forecast replacement windows. When they find a runner that has accumulated more erosion than modeling predicted, when the cavitation damage on a blade is progressing faster than the historic rate, they escalate the maintenance cycle, because a runner that fails inside an operating turbine does not fail quietly. At the rotation speeds and flow volumes involved, a catastrophic runner failure would release energy through the powerhouse that no design has been built to absorb. The penstock, the draft tube, the generator floor above, all at risk in a failure cascade. This is why the degradation models exist. This is why the inspections happen on schedule, whether the unit seems healthy or not. The goal is never to experience the failure. The goal is to ensure the conditions for failure never fully accumulate. At 6:30 in the morning, the control room shift changes. The incoming operator sits beside the outgoing one for 30 minutes. Logbook reviewed. Any anomalies from the overnight period discussed. The state of each unit, load, vibration readings, any unusual trend, transferred verbally and in writing. This handover is not bureaucratic ritual. It is operational continuity. The system does not pause between shifts. The turbines are still turning. The grid is still drawing power. The reservoir level is still changing, slowly by centimeters per hour at current inflow rates, but changing. The incoming operator must understand the system state as precisely as if they had been there all night. The outgoing operator waits until they are satisfied that understanding is complete. Then they leave, and the machines continue. The James Bay Hydroelectric Complex will not be decommissioned in this generation, or likely the next. The reservoirs are filled, the tunnels are cut, half the powerhouses are embedded in billion-year-old rock. The investment is fixed. What remains is operational excellence across a multi-decade horizon. The runners that spin today will eventually be replaced with more efficient designs. Modern runner geometries achieved through computational fluid dynamics modeling that didn't exist when LG2 was designed can deliver several percentage points of additional efficiency. On a machine generating 333 megawatts, at a 2% efficiency gain is 6.6 megawatts of additional output from the same water. At James Bay scale, these marginal gains accumulate to significant energy volumes over a year's operation. The engineers working on this now are optimizing a system that was designed half a century ago. They are not rebuilding it. They are refining it. There is a particular kind of discipline in that. In working to improve something that already functions, that already delivers, that was already built to a standard of engineering integrity that has held for decades. The La Grande River, below the last dam, still reaches James Bay. The water that passes through the turbines at LG1 continues north. It moves through the tail race, rejoins the main channel, travels the remaining distance to tidewater. At the river's mouth, where fresh water meets the salt of James Bay, the river ends. The river has been managed, divided, stored, timed, and routed. But it has not been stopped. The water still arrives at James Bay. It is colder in winter now than it was historically, in sections. Regulated releases from deep reservoir storage tend to be thermally uniform rather than seasonally variable. The biological implications of this are studied, monitored, and subject to ongoing mitigation commitments under the Cree governance agreements. The engineers who built this system in the 1970s could not account for everything. The engineers who operate it now are accountable for much that was not anticipated. That is the responsibility that comes with infrastructure at this scale. It does not end at commissioning. It extends indefinitely into the operational future. The powerhouse at LG2 is running at full load. The reservoir is at elevation 175.6 meters, within 2 meters of its design operating level for this time of year. Inflow from the watershed is below the long-term average for the month, a dry year, in hydrologically, but within the range the system was designed to manage. The 16 turbines are producing. The HVDC lines are carrying power south. Montreal is lit, and in the underground powerhouse, deep in the rock of the Canadian Shield, the turbines are turning, measured, continuous, reliable, and the sound they make is the sound of water doing work at the scale that engineering allows. Low, constant, and just beneath the frequency of ordinary hearing. Under this video, there's a subscribe button. It's a small action, but it helps keep stories like this afloat. If these systems fascinate you, the quiet force of water held in place by engineering and discipline, subscribing simply means you want to see more of what operates beneath the surface.